Hello, this is the next video in a playlist that I'm calling General Linear Models Design of Experiments, and this is part 8 of an 11-part mini-series within that larger playlist. And we're looking at hierarchical designs, and more specifically something that's called a 3-stage nested design. And here's a quick illustration. So we have 3 factors that we want to study, and factor A has 2 levels, and factor B nested within A has 3 levels. So this one and this one are really not the same. So we could have labeled them 1, 2, 3, 4, 5, 6. And then also within factor, and for more details on that, look at the first parts 1 through 6. I think the way this is nested. But we could also have a third factor that's nested within B. So these ones aren't really the same. We could label it 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 2, 4, 6, 12. And then within each of these levels, we have reps. So here we have 2 reps. So A is 2, B is 3, C is 2, N is 2. And within these, there's 4 indexes. The first one is 1, 1, 1, and the first rep. 1, 1, 1, second rep. And then that, and I repeat here, I just put dots because I kind of got lazy. So this one would be a 2, 1, 1, first rep. 2, 1, 1, second rep. And then it goes through. And so the model it's a linear model, so it's y equal to x star beta star plus epsilon, but it's partitioned into the grand mean, factor A, factor B, and factor C. But remember, factor B is nested within A, and factor C, or the third factor, is nested within B. And you might write it in scalar form as yijkl equal to mu plus alpha I plus beta j within I plus k within ij, right? That is these levels here. And then the air term is, you kind of think of it as nested within all 3 levels. And I is 1 to A, J is 1 to B, K is 1 to C, L is 1 to N. Now, I'm going to flip here because I couldn't get this on page 1, but the design matrix looks like this. So you order them within the levels. So the rightmost changes the most frequently, then the next. So this column of X deals with the mu parameter. The next 2 columns, and there's only 2 because it deals with factor A, and there's only 2 levels. And notice that all these, start with a 1, and that corresponds to this. And then the next, the next group starts with a 2, which corresponds to this. And those deal with the alpha 1 and alpha 2. Then the next columns deal with factor B. But remember, there are 6 different levels. So it's 1, 2, 3, 4, 5, 6. And then, but we just label them 1, 2, 3, 1, 2, 3 in the model, but really they're separate. So there's 1, 2, 3, 4, 5, 6 betas corresponding to that. There's 3 nested within 1. And then there's 1, 2, 3 nested within level 2 of factor A. And then for factor C, the third, each of those 12 get their own parameter. And so this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. But we call them 1, 2, nested within factor level 1 of B, 1, 2 nested within factor level 2 of B, and etc. And then they get their own parameter. Gamma 1 nested within 1, 1. Gamma 2 nested within 1, 1. Right? So this gamma 1 is nested within 1, 1. This gamma 2 is nested within 1, 1. This gamma, this would be gamma 3, is nested within 1, 2. This gamma 4 would be nested within 1, 2. So that's why there's repeats. 1, 2 nested within 1, 1. 1, 2 nested within 1, 2. 1, 2 nested within 1, 3, and etc. Okay. So look at the structure of this design matrix. It's basically ones down the diagonal. You know, it's a vector, the same. And there's only 2 columns, so it's 1. And then there's 1 column. So the perpendicular projection matrices onto these subspaces are going to be similar. And that's what we look at next. So the perpendicular projection matrix onto the column space of 1, you know, it's 1, 1 transpose 1, inverse 1 transpose. And it has this structure. It's 1 divided by A, B, C, N, and this, the U is a square matrix of A, B, C, N of all 1s. So really this is a constant matrix of 1 divided by this. The perpendicular projection matrix onto the column space of X alpha is defined this, and it ends up being a block diagonal of 1 over BCN. Right? And the structure for the next ones are going to be the same. M beta, you know, defined like this, is block diagonal of 1 over Cn. And then M gamma, defined as this, you know, X gamma transpose, X gamma inverse, X gamma. These should all be transposed. Transpose, and that should be a beta. And it's, so M gamma is block diagonal 1 over N. And it's the perpendicular projection matrix onto this space. And how we create these is, note that, and this is just a brief reasoning. So 1 is in the column space of X alpha. So we can write it like this. Column space of 1 is a subset, it's a subset of the column space of X alpha. So we can take the perpendicular projection matrix onto X alpha, which is this, and subtract the perpendicular projection matrix onto the 1. And then it's the perpendicular projection matrix on the orthogonal complement of column space of 1 with respect to X alpha. Right? So the column space of X alpha is this, but then we can get rid of some of these columns here and make all these orthogonal to 1. Then since this column space is column spaces that are orthogonal, then it's the addition of those column spaces. So this is J, and then this, remember, it's orthogonal to 1. So the perpendicular projection matrix is M alpha minus J. So you add those, but really you just get M alpha. And that's what we were saying it was to begin with. But this is kind of a different way to develop it. Column space of X alpha is a subset of the column space of X beta. So column space of X beta is still this, because each one of these is within this column space. But you can create little column spaces so that are orthogonal. So these columns are orthogonal to 1, and then you create these columns are orthogonal to these, right? So they're all orthogonal. Then this here is really just a column space of X, and it's orthogonal to this. So the perpendicular projection matrix is M beta minus this one, and because we're doing it on X beta star, which is all orthogonal to this, and that's what this is defined. So it's a perpendicular projection onto this orthogonal complement space with respect to X beta. And then we can do something very similar for the X gamma column space. So the column space of X beta is a subset of the column space of X gamma, but column space of X gamma can be thought of like this, where you create little, little columns, and they're all orthogonal to each other. Oh, and this should really be the column spaces, or orthogonal. Then you just create a perpendicular projection matrix. Since this is a subset of X gamma star, then you take the perpendicular projection matrix onto this minus that, and that's the perpendicular projection matrix onto these column spaces. But then you can create column spaces. These are all orthogonal, so it's the addition of those perpendicular projection matrices. J, M alpha minus J, M beta minus alpha, and then this is M gamma minus beta. But notice that they all cancel and just equals M alpha. And that makes sense because the column space of X gamma is actually equal to the whole column space. So it makes sense that these perpendicular projection matrices are equal. Now, to create the sum of squares error, we use those column spaces that are orthogonal. So the total can be partitioned into sum of squares for factor A, sum of squares for factor B nested within A, sum of squares for factor gamma nested within B. And it starts out with the total sum of squares, and like doing this in matrix notation. Then we can add and subtract M. And then, but we write M in this form here. And then this J will cancel with the J on the previous page I'll show you. But then these right here partition that sum of squares total, right? The J would cancel with this one. And that's sum of squares A, and that's the sum of squares for B nested within A, and that's the sum of squares gamma nested within B. And it's so crazy that when you use these matrix notation to calculate the sum of squares for alpha, beta, and gamma, it's equal to what R produces, or any software. And to me, it's just so cool how that all works. Okay, well, that's all I'm going to cover for three-stage nested designs. Hopefully you enjoyed that. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.